Good afternoon. So let's start. This is a tutorial. It's called Unlock the Future of Kubernetes and Accelerators with Dynamic Resource Allocation. My name is Rey Lejano. I'm from Red Hat. I've been a Kubernetes release lead for 1.23. I'm a maintainer as the SIGDocs co-chair, one of the co-chairs. I also help run the third-party security audit for the Kubernetes project as well. The reason why I like studying new features, diving deep into new features Kubernetes comes from working on 7 release teams, and also as a docs approver, I review docs pull requests for every new feature that goes into the release 3 times a year. Do want to make note, this is a hands-on lab as well. So most of the time we're going to be in a terminal. We'll have links for the lab environment and for the GitHub page. For the GitHub pages at the end of a few slides here. But I do have handouts on the very front table on the right here and the very front table on the left here with the blue bottle. And that has URLs for the lab environment and also for the walkthrough. But I will walk through all the steps. If you just copy and paste all the commands, it'll take about 30 minutes or less. But I do want to spend some time into diving into the DRA resources, because that's why we're here. And if you've attended the keynotes, you've seen that the Kubernetes AI Conformance Program, version 1.0, was released. Is there not shown on the screen? Oh, there's. And it was also announced back in KubeCon, Japan and China. And the very first must in the Kubernetes conformance for AI is that DRA must be enabled. And DRA is a feature in Kubernetes that was released in 1.34 that allows you to request and share resources among pods. And you can share other devices as well, and we'll go into that. And you could also filter devices with common expression language that we'll see, and you could organize devices. Let's say if you want to say a set of group of devices is cost optimized versus high performing. So we'll dive into how we do that in the lab. I'll give a few minutes. I see folks walking up here to get a handout. I do want to make a note on the handout. It does say the VMs will go away at a certain time, but they will actually go away much sooner, a few hours after this talk. So the old way is device plugins. So we use device plugins before 1.34, unless you're using the beta APIs for DRA. So you use device plugins to have your pods access hardware like GPUs. And you request GPUs in a pod spec similar to where you would request CPU and memory limits. So that's in your the containers.resource for your limits. And limits equals request. We typically use node feature discovery as well to find PCI. It typically does the ls PCI and then labels your nodes appropriately to use for node feature discovery. And back with device plugins as well, you would install several host components and Kubernetes components as well. And so like the NVIDIA Container Toolkit and node feature discovery, like I mentioned. There is a device plugin, and there's also a Kubla plugin we'll see in Dynamic Resource Allocation as well. And for some metrics, we have the DCGM exporter. And also you could also have a MIG manager as well to partition your GPUs or use vGPUs as well. So why change? Well, we want new capabilities and features to access our devices, not just GPUs, but also NICs as well, FPGAs, and also network-attached devices. And we want new features like we could pass configuration parameters to those devices. Like I mentioned, we could do fine-grained filtering with common expression language. We could share devices amongst multiple pods. We can before, but you had to go with time slicing, MIGs, or vGPU. And we have a centralized device categorization as well. And also, one of the key features is the pod is scheduled when the required resource is also available, instead of having the pod failing on a node if the resource is not available as well. And you can do cool things with DRA, with this NVIDIA GB200 NVL72 with 72 NVIDIA Blackwell GPUs. And so you can use a rack of GPUs in the cluster and workloads. So common difference, or the differences in how you would use a GPU within a device plugin versus DRAs is in the left and the right. At the left is the device plugin. Like I mentioned, you would add it into your resources in your pod spec. And we see here with limits, nvidia.com/GPU and number 2. With DRA, you could also have multiple. Also can think of how storage is provisioned in Kubernetes as well with PVCs. Here we'll go into the resources later on, but here we see the resource claims for a shared GPU and an inference GPU and how we use them in the pod spec under claims. This just goes into a little bit more of the sharing for multiple pods. We have 3 different pods sharing the same resource claim here. We'll take a look at this more deeply in the walkthrough. And a DRA driver, so it's always from the vendor. There's 2 components from it. We'll touch base on the controller part in a little bit, but first there is a node local kubelet plugin that's typically a daemon set. That's where the driver binary is at, and that kubelet plugin advertises the node local state of the devices. It also helps configure those devices as stated by the pod, and also pass those devices requested to the kubelet, and it'll forward it to the container runtime. We'll go back to the controller a little bit. We'll touch base on some of the resources as well. First is the resource slice, which is created by the DRA driver. It's sort of bound to the node, and the resource slice is what represents those devices represented by that driver on the node. And it's used by Kubernetes to help find nodes with devices for scheduling pods so that nodes can access those requested devices. Device class, if you can think of like storage class, defines category of devices like gpu.nvidia.com. You can add in parameters as well in device classes to match devices in resource slices. So a resource claim is a request for those specific devices from a device class. And a resource claim is referenced by multiple pods, or can be referenced by multiple pods if the device can be shared and not bound to a pod's lifecycle. So there's a difference. So resource claim template is a template to generate per pod resource claims. So if you use a resource claim template, it will generate a resource claim per pod, and if the pod dies, then the resource claim from that resource claim template also dies as well. And we go back to the controller, and that is what helps to perform that creation of the resource claim from the resource claim template as well. It also helps perform deallocation of resource claims as well. And also, do you want to make note there is a scheduler plugin as well that detects pods, which references a resource claim or a resource claim template and helps ensure that the resource is allocated where the pod is scheduled to. And go through several diagrams or iterations of this diagram. So usually, this is kind of like the workflow here. The first one is the cluster admin installs the DRA driver, which includes that node local kubelet plugin as a daemon set and a controller in a deployment. Then from that, a resource slice is created that represents the devices on the node. The DRA updates the cluster with what devices are available to the pods on the node by publishing that information on the resource slice. The cluster admin then creates the device class, but the device class can also be created by the DRA driver. And so that is a step that's required. And also the cluster admin does create certain RBAC that we will create during the walkthrough, like a service account, a cluster role binding, so that the certain resources can get like resource claims, can get nodes, and also like in the plugin can also have full lifecycle control of the resource slice as well. And then cluster admin creates a priority class as well to make sure that the DRA driver it prevents it from preemption of the DRA driver. So we will create a priority class in the walkthrough. Next is the workload operator will create the resource claim template or resource claim, and that will request specific device configurations from a specific device class. Then the pod is created by the workload operator, and the pod references that resource claim template or a resource claim. And the cluster checks for new workloads that refer to resource claim templates or resource claims. And if a resource claim template is used, like in this diagram, then the controller generates a resource claim per pod. And for every pod, the cluster checks all resource slices to find a device that satisfies that node in the pod and make sure that the pod can have access to those devices so that the node is eligible for that pod. And lastly, so after finding an eligible resource slice for a pod's resource claim, the scheduler updates the resource claim with allocation details. Scheduler places the pod on the node that can access those allocated resources, and the device driver and the kubelet configure the device and the pod's access to that device. All the steps we talked about is all here on notes. It's in the slides. Slides are already updated on Sched as well. So we're going to go in the lab, and there's 4 modules. Like I mentioned, there is, it's going to take, if you just click through everything, it's going to be 25 minutes. About half an hour or so. But I will walk through each step with everyone as well. And before we actually go into the lab, there's our thank yous, especially the folks who contribute, or DRA, Patrick Oley, who's here from Intel, Kevin Clues from NVIDIA, John Belarmick from Google. Also want to thank Red Hat for the VMs. We definitely have a lot of VMs, so everyone here can have their own VM to access the walkthrough. And to access the tutorial walkthrough is dra-tutorial.cloudnativeessentials.com, which forwards you to the GitHub page here. Like I mentioned, there are handouts on, it looks like we ran on the left, but there's some more on here on the right table here. The VM access is dra-lab.cloudnativeessentials.com, which in both them forward in case there's some DNS issue as well. And the GitHub repo for this is github.com/cloudnativeessentials/dra-tutorial. So I'm going to walk through slowly because I know it takes time for folks to access the virtual machines, wait for clusters to come up. I have a easy bash script that folks could curl, and that will install the cluster and get it ready for you. So I'm going to walk through that. I'm going to change my mirroring here. All right. So I'm going to have this up for now, and hopefully folks can see that still. Oops. So that VM access URL brings you to this page on the left. And here you put on any email. It doesn't have to. We don't track any emails. Everything will be deleted a few hours after this tutorial. Put in a password here, which is RHKC 2025. If you do go to the GitHub page, there's a link to the demo platform as well. So access this workshop. So you have access to a virtual machine that's only yours as well. So I'm going to copy the login command. Later, I'll copy the password here. This is all in the walkthroughs. I'll get to that in a little bit. Just want to get folks started getting access to the virtual machine here. Hopefully, this is big enough. I can make it a little bigger because I'm going to be doing a lot of command line. Hope folks like command line. So it's going to be mostly command line. So I'm going to get my password ready as well. Accept it, enter the password, and I am in my virtual machine. I'm going to give folks a few minutes here, and then we'll continue on. I'll go through the walkthrough pretty slowly here, but you could continue in your own pace. Once again, the links is dra-tutorial.cloudnativeessentials.com for the GitHub page for the lab walkthrough, and the VM access is dra-lab.cloudnativeessentials.com, and there's some more handouts here for those links here. Give a few minutes for folks. Let me put this on the left side so it's up. Well, I'll go through the first few steps. So this is the GitHub page. The first part is just the abstract. And so the goal of this tutorial is to install a Kubernetes cluster, review those DRA resources, and see how they work. We will install a sample DRA driver, run workloads. They're going to be Llama that use that DRA driver. These are VMs. There are no GPUs attached to them, so we will use an example DRA driver, but we will add in the same steps as if you were going to use a GPU. I came away with creating this tutorial with what I wanted as a user to learn about. So we will do a lot of introspection into the NVIDIA, Intel, and DRA-net DRA drivers, because I know that after a DRA tutorial, folks want to see what NVIDIA's or Intel's DRA driver actually looks like. So the first half of the walkthrough is actually going to be a lot of introspection into the DRA resources. Then the last part, which will probably take less than about 40 minutes or so, will be actually deploying that DRA driver, deploying workloads, creating RBAC that's needed. And then we will take a look into see multiple ways of deploying workloads as well. One's with the resource claim templates that we'll deploy. Then we'll use a job for that resource claim template to deploy multiple resource claims when those job pods come up. And we'll dive into as well, see what GPUs are assigned to the workloads and the pods. Because I believe the example DRA driver has like 8 or 9 GPUs. So we'll take a look to see how that's allocated and how we could take a look to see. And we'll take a look at the logs as well for the DRA drivers, kubelet plugin as well to see where the allocation is performed. So the first one is cluster setup. We'll do a little DRA overview again. There is a lot of repetition because I believe the best way to learn is by repeating and hands-on as well. Then we'll look at DRA under the covers, which is looking at all the DRA resources. Then we'll look into NVIDIA's DRA driver, Intel's DRA driver, DRA-net. Then we'll deploy a DRA driver and several workloads as well. And so we'll go right into that. Hopefully I'll go slow enough that folks can follow. You can also use these steps as well. Use the same bash script if you have this one's specifically for Rel 9. Or from that bash script, you could create your own script to install a kind cluster as well. So a little bit on DRA, as we mentioned, it was released in 1.34, which was released a few months ago in August. And the core DRA component was promoted to stable. There are many DRA features coming up, so look out for those. And DRA, like we mentioned, is a new API for pods to access accelerators, GPUs, TPUs, network-attached devices, and also it kind of, I've seen a talk before where DRA is referred to as device plugins 2.0. I'm going over the benefits of DRA already, how you could filter with common expression language. We'll look at that. You can share amongst multiple pods, devices with multiple pods. We will take a look at that. We could do flexible configuration, and also and we could pass configuration parameters to devices, and it'll work not just on GPUs, but other types of devices as well. And DRA, you will install a kubelet plugin that talks to the node's kubelet about the device and prepares that device to be used. And also, like I mentioned, that DRA driver will create a resource slice object, which we will take a look to, so we could take a look at what devices are available on that pod. Device class, similar to storage class, and device class has those device configurations as well. And if a pod wants to use a device, a user creates a resource claim or uses a resource claim template that refers to a device class. And the cluster admin installs the corresponding device class that has those device configuration and selectors for that device. So this is the link to the workshop platform. Hopefully, folks have been able to log in into your virtual machine. This one is 2 CPU, 8 gigs of RAM, just running on kind. So you stage as you would normally in this example one. Don't copy and paste this one. I apologize, there's no click to copy here, so you do have to copy and paste manually. But now I will walk through some of the first few steps here. So we already logged into our virtual machine. We will run an install script. This will take about 3.5 minutes to install a kind cluster. So I will let that run here. Also installs Helm as well, Docker, Kube control. If you actually dive into the kind cluster, it also exposes some ports as well and YAML configuration for the kind cluster. But we won't actually use them. But I did those just in case, like the Llama port. So we'll let this run here. We'll have folks catch up a little bit, or folks that want to go ahead, feel free to. The next steps here are just testing the cluster. We do kube control version and get nodes just to verify it's around 134 as well. So the first few steps is just testing out the cluster. Then we'll go into looking into a DRA driver and DRA resources first. Then we'll go into looking into a specific vendor's DRA drivers. So give a few moments here. Any questions so far? All right. Any problems accessing your virtual machine? All right, all good. Should have started this a little bit earlier, so give it some time, but I'd like to give folks plenty of time to catch up or to go ahead so they come up with any, so they could have create any questions when needed. All right, it's almost done here. Oh yeah, JQ is also installed as well. The last few steps are just a cluster coming up and also Helm installation as well, because NVIDIA has their DRA driver in Helm, same with Intel as well. So we're almost there, creating a kind cluster. Yeah.
Does it need the NVIDIA notification discovery driver?
Yes, for labeling, but yes, for labeling, yes. Because you want to, yes and no. I've seen it where use cases where like if you need nodes to be labeled in a certain way, but I've seen it used with NFD before, yeah.
Does not need the NVIDIA operator?
For this one, no. It does not need the NVIDIA operator. There's the NVIDIA DRA driver you do need. But yeah, it's, because I've seen DRA used without NFD as well, so I want to say it depends, as usual, but I've seen it used and referenced with using NFD as well, because it does use labels. And we'll look at that in the NVIDIA DRA chart, because we'll see that it will actually try to, we'll use certain node labels. That's from NFD. NFD will apply those nodes, will apply those labels. All right, checking the cluster here. Let me move this back on top here. I'm trying to be good and clean up version here. 134, keep CTL, get nodes, just make sure 134 as well, so we're good with that. So like I mentioned, there's a lot of repetition, because I believe repetition is a good way for folks to learn. DRA driver has 2 components, the node local kubelet plugin, which will be a daemon set, which we will take a look at, and a controller running as a deployment. A centralized controller performs that resource claim creation from the resource claim template. Also performs deallocation as well. And that node local kubelet plugin performs passes the configuration of devices to the kubelets and to the device, and gets that pod working with that device as well. This is a repeat of the architecture that we had from the slides. This repeats the same exact information, has the DRA driver having 2 components. The resource slice, which is created by the DRA driver, it's tied to the node, represents the devices that's representing that by that driver on the node. And it's used by Kubernetes to find the nodes with devices that pods requests for. Device classes are like storage classes, defines a category of devices like gpu.nvidia.com. And you have your resource claim as the request for the specific device, and a resource claim template. It's a template to create a resource claim. So we'll do a lot of kube control explain just to reiterate these definitions. Then I'll do these quickly, and then we'll go into the actual deployment introspection of NVIDIA's and Intel's DRA drivers because of time. So that is for resource slice. It does represent one or more devices in a pool. And here's an example of a resource slice here that we see here. We see that the name, the driver, the gpu.nvidia.com, the pool name as well. It could have multiple pools. This is specific to a node, so node 1. And we have devices with attributes like vendor, model, memory. And we'll use memory quite a bit later on as well. Device classes are like storage classes. So they correspond to the resource driver with the named resource in the cluster, and also some predefined selection criteria for those devices. So let's do a kube control explain here for those device class. So it is given is a vendor or admin provided resource that contains device configuration and selectors. An example, a very simple basic device class is just name gpu.vendor.com here. And the device.driver equals to gpu.vendor.com. But we could example here of, we could use multiple common expression languages as well for that CL expression, not just the device.driver. We could add in attributes like type GPU, accelerate type. This is where we could categorize to like high performance or cost optimized. So we could add in those specific attributes into that common expression language selector and expression there. So later on, we'll look into Intel's. This is Intel's example of their device class here. Has a device.driver equals gpu.intel.com. The extended resource name is an additional way for pods to request resources. It is listed as alpha as in 1.34. And you could take a look at the resource names in kube control explain as well. So resource claims is how we request for those devices by pods or by the resource claim template. So I'll spend a little bit of time here just to review once again. So we'll look at kube control explain here. And the resource claim is that request for access to resources or devices by pods. And resource claims can also be created from these resource claim templates, which we will take a look at. An example resource claim here, is a very simple example, is just the request. It has that device class that we are referring to. So this is referring to the same exact device class that we use in example, just gpu.vendor.com, and the common expression language. In this example here is memory quantity 80 gigs, and type is GPU. So for this resource claim, it creates those devices in the gpu.vendor.com, or you request for those devices, and has to satisfy both parameters of device driver.vendor.com type equals GPU, and also the value of memory equals ADGI. Resource claim templates, this is a very short description of it, is that template to create resource claim objects. So we're going to look into DRA drivers, actual DRA drivers right now that's published. And the first one is, of course, NVIDIA, the most popular one. So NVIDIA's DRA driver is installed with a Helm chart. So this step, you will add the repo, NVIDIA's Helm repo here, and also do your Helm repo updates. And the next few steps has a lot of output. And the reason why I added those steps is just to show how someone can introspect a Helm chart and understand what is being installed. Instead of doing Helm install and not knowing what is installed, this gives you several ways to dive into a Helm chart. If you're not familiar with Helm charts, so we could take a look at NVIDIA's DRA driver Helm chart. Let's just show the chart first off here. We see the version. Next few steps is going to be a lot of output, and I'll just highlight some key ones as well. And a note here for NVIDIA's DRA driver, you will see a lot of references to compute domain as well, even in the device class. So what compute domain is, it's when workers will request a compute domain, then NVIDIA's DRA driver for GPUs work to share the GPU's memory with NVLink, which is a high-speed interconnect for GPUs. So you will see compute domain quite a bit in NVIDIA's DRA driver. So Helm show value shows what you can configure when you do a Helm install. So this will just go into the Helm, what you can configure in the Helm when you install NVIDIA's DRA driver. I'll just point to a few little. I won't point to anything for this one, but we'll dive into see some of the components here. Mostly with the controller that we saw before, and with the kubelet plugin, and that's a daemon set. We see these in the Helm chart. And Helm show all shows off everything. I'll do this briefly just because of time here. I won't go through every single one because we have a few more to review than actually deploy a DRA driver. So Helm show all looks at everything for the Helm charts here. And I'll point out what the key ones in a little bit here. We'll do some filtering here with grep. So we'll go through all of these just for the sake of time here. Like what I showed off before, we talked about the controller for the DRA driver. And we see that with this grep here, we could grep for controller and see where some values are for that controller. Same with the kubelet plugin as well. So here we see this, the kubelet plugin daemon set here has configuration for that daemon set for the NVIDIA's driver. And of course, we're not going to install NVIDIA's DRA driver. We do not have GPUs on these virtual machines. Let's just do a dry run. So we can take a look, see what actually gets installed here. And then we'll go through this very quickly. I won't go through it, all of it here. But here we can see the RBAC configuration we need. And like I mentioned, we will see compute domain quite a bit in NVIDIA's DRA driver. We have service counts. We have cluster roles, cluster role bindings as well. I go into more detail in the walkthrough if you want to spend some time. I know we don't have much time. I do want to spend more time on the actual deployment of a DRA driver. So let me just go through this a little bit here. This is the actual deployment of that controller that I mentioned here, that it is deployed HA, so it is a deployment here. Here's the device class for NVIDIA's. Like I mentioned, it will say compute domain as well. So we'll see compute domain instead of GPU or driver.gpu for NVIDIA. So that's something to look out for. And this is a list of what NVIDIA's DRA driver Helm chart action installs. In the namespace, 3 service counts, 3 cluster roles, cluster role bindings, the daemon sets for the kubelet plugin, the deployment for the controller, 2 device classes, and some emission policy as well. Now we'll look into Intel's DRA driver. It's also installed with the Helm chart as well. And we're going to do a dry run just to see what gets installed here. Oh, there is a missing A, H. So here is Intel's DRA driver. Like with NVIDIA's, we install some RBAC, service count, cluster role binding. Here's that daemon set for that kubelet plugin that is part of the DRA driver, has a binary for that DRA driver. And then we'll take a look to see if the deployment is shortly afterwards here. No, it's a device class. So Intel's device class is gpu.intel.com and has an extended resource name so pods could use to reference it in the future. Some emission policy as well, and we'll go and see that. So this is just summarizes what Intel's DRA driver installs. Some RBAC, that kubelet plugin daemon set, your device class deployment. And I wanted to put in an example of a DRA driver that is not a GPU. So Google released DRA Net. It's a Kubernetes network driver for high-performance networking. There is a white paper out, and you could find more information on the GitHub repository here on both sites here. There's also the doc site for as well for DRA Net. So the DRA Net driver communicates through the DRA API and the container runtime via the NRI, or the Node Resource Interface. So when the pod's network namespace is created, the container runtime initiates that gRPC call to DRA Net with that Node Resource Interface. And unlike the other DRA drivers, the DRA Net is actually installed with a YAML file. So we'll take a look to see what the YAML file has. There's a simple curl command here. And I'm just going to go briefly through it here. As we saw in the NVIDIA and also Intel DRA driver, we always start off with RBAC, which we will do an example as well. So service count, cluster role binding here. I think I missed some here. There's a daemon set for the plugin. And then if you want to actually take a look, see what is installed, you could do a kube control apply and just do a dry run client here. So that we'll do that here. And we can see those, those resources actually deployed. So, all right. Apologies if that was fast, because I wanted to actually spend some time on actually deploying a DRA driver with everyone here. So, more on DRA Net. Here's the sample. This is how to create the device class. So this is an example where the DRA driver does not create that device class. So you would have to create that device class, and this is a sample one that's given by Google here. We can see the CL expression for that device class here is just with just device.driver equals DRA.net, and the expression and the attributes is just cloud network. So you could use DRA Net for GKE clusters here. Here's an example resource claim that you would use for a pod to request to use DRA Net with that filter or that selector, using the same cloud network attributes as well. This example is giving a VPC. And this is the pod example on how you would use DRA Net and reference a resource claim in your pod spec here. You would just use resource claim name as well. So we are actually in the last module, which is where I want to spend most of the time here, and walk through all the steps here. And we are going to deploy an example DRA driver. Like I mentioned, we do not have GPUs, so we will simulate GPUs by using the example driver. First, let's create the namespace. Keep it all nice and clean in a namespace. And we're going to create the device class. So before each step of creating a resource, we're going to actually curl and take a look at that manifest, so we could take a look to see what we're installing before we actually install it. So let's curl this device class manifest. And it's very basic. Just gpu.example.com, device driver equals gpu.example.com. So I do have comparisons if you want to remember what NVIDIA's device classes and Intel's device classes were. Device class for NVIDIA had a few more attributes, and then Intel's, it was a little bit more like our example DRA driver here. So let's look at Intel's device class here. So Intel's just has the device.driver equals gpu.intel.com. It just has the extended resource name. So we looked at our example device class, so let's now install it. Let's do kube control apply here. Device class for that is gpu.example.com is now created. And before we could actually deploy our DRA driver, let's actually deploy some RBAC authorization so that the driver can control resource slices, control the full lifecycle resource slices, get nodes, get resource claims. So we're going to take a look at a manifest with all 3 service accounts, cluster role, and cluster role binding here. So we have the service account, it just DRA example driver service accounts with some labels, and we have our cluster role, just the get resource claims and get nodes and full lifecycle of resource slices. And we have the cluster role binding that binds that service account and that cluster role. So let's create it. Keep control applies. So now we have the service account, the DRA example driver, and for the cluster role and the cluster role binding created. And of course, we don't want our DRA driver to be preempted, so we want to prevent preemption with a priority class. So let's just add in a very simple priority class with the value of 1 million. And let's just create that priority class. All right. So now we're actually at a point to deploy our DRA driver. Let's take a look at what we're actually deploying. So we're going to take a look at the manifest here. I'll go on the right side here. In the namespace, DRA tutorial, this is the daemon set for the kubelet plugin here. But I won't go into more integrated detail here. So we're going to create our DRA driver and the daemon set here. We have the daemon set created here. We're going to check the status of the daemon sets and also the pod as well. So keep control, get daemon set and pods for the DRA tutorial using the label app.kubernetes.io/name, the DRA example driver. So our pod is running. Now we have our driver is running as well. Now let's take a look to see what devices our DRA driver is actually has. So we get our resource slice. We see a resource slice was created 30 seconds ago. We did not create the resource slice. It was created by the DRA driver. And let's take a look and describe it. So we see several GPUs. We have GPU. In this example here, and this node here, we have several attributes. Let's just go from the top here. Devices, this is for driver version 1.0. The model, latest GPU, memory 80 gigs, and then several GPU 8s, and we iterate from GPU 0 to GPU 8 or 9, I believe, and they all have the same models and values as well. So fictionally, we have many GPUs on this node, and now we'll try to use one or several of these GPUs from pods or by pods. So before we can actually use our device, we have to create that resource claim. So let's take a look at the resource claim that we will use to create. We see here that we are using the device class that we just created, and we actually have the same selector as well. I'm sorry, we don't have the same selector. We do have the device capacity here for ADGI. And so now let's create the resource claim. I do want to make a note of the allocation mode here, exact count. So this means that if a pod uses this resource claim, it will give you exactly one GPU or one device that satisfies that expression. If you use all, and I have an example here because I've done this as well, it will actually allocate every single GPU that satisfies the CL expression. So I'm going to keep control apply. That resource claim is now created. We're going to get that resource claim and do keep control get resource claim. And note that is a state appending. And we could describe the resource claim as well. And note that it's the same quantity. It's asking for GPUs from the device class gpu.example.com with a quantity of 80 GI. We'll take a look at a few. We'll go back to this resource claim to see how it changes as well when we actually have a running workload. So let's deploy some actual workloads. So we're going to use Ollama. Ollama is a tool that runs LLMs locally. And llama.com actually hosts many LLM models as well. So the first one, we're actually going to deploy an Llama pod that will not use GPU, not require GPU, just the Alpine Llama image. If you want to use a GPU, you could use the Llama/Llama container image as well. So let's introspect the pod manifest that we are going to create. So we see here we're using the image, Alpine Llama. We are exposing some ports for its container 11434. And here we see we are using the resource claim name example-resource-claim, which we just created, giving it a name GPU, and we're adding that into the container under resources.claims with name GPU. So we will create the pod here. Pod's created. Now let's go back and check that resource claim that we created and see what that looks like. Let's just do a get. And now we see it's allocated. Remember before it was pending, so it's now allocated and reserved. So if we actually look at the resource claim itself, the first thing we'll see here is that we have reserved for, or we have a status, the allocation for GPU-8 in my example. Yours might be different, and is reserved for a pod, this Llama pod. So so like I mentioned, if the allocation mode was set to all for the resource claim, this is just an example of what that will look like. Well, under status, it will actually say every single device that satisfies that CL expression for your selector for that one pod. So this example, if you put allocation mode into all versus to count, and for this one, we use 1. So let's take a look at some logs for that DRA driver and see the actual allocation here. So we see here that GPU-8 here is allocated for that pod here. So if you have any troubleshooting with DRA, you can always check the logs of your driver as well. We're going to check the Llama pod, and of course, we're going to run a query to Llama using a few LLMs as well. And for this example here, we could check the environment variables and actually see where the GPU device here, GPU-8, how it's sharing strategy, time slicing as well. So this indicates how the GPUs can be configured, and also how it's also injected into the pod as well. So now let's actually pull the Llama 3.2 LLM. This might hopefully not take too long, but I know the next step is going to take a while, so I'm just going to kick it off. We're actually going to ask Llama 3.2 what is Kubernetes, and that will take 4 minutes, and we'll compare with another in the same pod as well. And as you can see here, the Llama LLM is quite large here, so we'll try to use a smaller one in the next round. So this will take about 4 minutes here, so I'm going to let it run. I should have ran a smaller query, but of course, we're asking what is Kubernetes. We're seeing what Llama 3.2 comes back as. Have example output, which might vary from what you get here, or it might be exactly the same. So far, it looks like it's very similar here. So I'm going to run through that and walk through the next step as Llama 3.2 is coming back with an output for our query. Llama 3.2 is 2.0 gigs, and so we want to, let's try using a smaller model like Tiny Llama. So Tiny Llama, I forgot the exact size of Tiny Llama, but I think it's under a gig here. So we're going to repeat the same, in the same exec pod here. We're going to do kube control exec and pull Tiny Llama. And we'll pull it, and we'll run the same query to see if there is a difference. This also gives us some time for folks to catch up or if they have any questions as well. I'll briefly stop here once the LLM is answering this question. Any questions? Oh, question there? Oh, what was that? Yeah. So the question was, I believe, what was the environment variables to the pod? So Kubernetes, is that what? It's by Kubernetes. I don't remember if it's the controller itself. It is by the control plane, or I don't remember if it's the controller, but Kubernetes injects environment variables like you see here, like the Kubernetes port, the host name. These are all from Kubernetes, and this is also as well from how, but I believe it does come from the driver, but it does come from the driver, but it does go to the controller, and I believe the controller goes to the API, which then injects those environment variables. But yeah, oh, I have to confirm with that and the workflow on that though. Yeah, yeah. Okay. What was that? Yeah, this is CPU. So the question was if the Llama is running CPU. Yeah. The Alpine Llama image just needs CPU. That's why it's running kind of slow here. And we'll see the Tiny Llama one will much less output, but also run much quicker as well. And we can see here the Tiny Llama is 637 megs as well versus 2 gigs. So, and does it provide a good enough answer for us compared to Llama? And that's up to, it depends, of course, on what you would expect and what you want as an output. So this hopefully is done soon. So I'll just pull the Tiny Llama model here. Llama 3.2 is very verbose, of course, but for 2 gigs, of course, you want it to have a good answer. So after we pull Tiny Llama, actually I may not go through this step, I'll probably do later. I do want to show example on how we could share this resource as well. So I'll probably jump a few steps here because we still have about 25 minutes here, so we still have some time. So I'll pull Tiny Llama here. It definitely is a little faster than Llama 3.2. Has anyone experimented with DRA so far in their clusters or? Okay. All right, I'm just going to clear this out. The output is ready in the walkthrough here. So we're just going to pull the Tiny Llama LM here. And we're going to ask the same exact question here. Using the command llama run. And what is Kubernetes, and let that go. It's going to be much shorter outputs. Of course, your responses might differ. But we're going to take a look at the next few steps here. So the beauty about DRA is that you could share resources. You could share resource GPUs by other ways as well before, like vGPUs, MIGs. But this is a little bit more easier way to share devices. So we're going to wait for this to finish here. So the next step is adding a pod, creating a pod that references that same resource claim. And we're going to check the pod, and we're going to check how that resource claim, the status of that resource claim, to see that 2 pods are now using that resource claim. All right, thank you, Tiny Llama. And this is just another pod using the same exact resource claim, and also using a llama as well. To keep control apply. And we're going to now describe that resource claim. So now under status here, we see GPU 8. We actually see both pods under reserved for Llama and Llama 2. And we'll take a look to see how you using a resource claim template differs from using a shared resource claim. Of course, this claim is just for GPU 8, so it's going to share GPU 8 with any pod that asks for that resource claim. So if we take a look at the environment variables, we'll see it's here as well, GPU 8. I'm going to go into the resource claim template because I think that's interesting how you, instead of sharing GPUs, we'll take a look to see how resource claims are created and how devices are allocated to multiple pods, but in a different way. So a resource claim template is just a template to create resource claims. So it'll look very similar to our resource claim. We're using an exact count as well, just one, and with the same selector using ADGI for memory for that GPU.example.com device class or device. So I'm going to keep control, apply that, and create it. So now we have a resource claim template created. We're going to use a job to actually, well, let's take a look at the resource claim templates to create multiple pods, because in theory, folks in HPC or batch will be using jobs most likely. So we'll take a look into how we use jobs with a resource claim template. And so here we have a job here. It's just going to be for completions using our resource claim template, and with that, giving a name resource claim, which we pass on to resources under claims, that same name. All right, we're going to create the job. Job is created. Let's take a look to see. Let's do a get jobs and pods and resource claim as well. So we see the job running, 0 out of 4 completion. We have 2 in parallel, so we see 2 jobs running. And we see instead of 1 resource claim, we see 3 resource claims. We see the resource claims tied to the job pods as well. So we're going to describe each new resource claim just to see what it outputs here, and of course your values will vary here. So the first resource claim, we see this is for GPU-1, and now we see the pod for one of the jobs, and if we see the other resource claim name, now we see GPU-0 instead of -1 or -8 as we saw before. So now we see using different GPUs and reserved for the pod. So let's get the pods as well, and we'll take a look at the pods just to confirm it has separate GPUs assigned to it. Need a space. So this is GPU-1 here. And for this one, this should be GPU-0. And we see it as GPU-0. All right. So want to spend some time as well as talking about a few other DRA drivers. And that job that we saw here will go into completion after some time. So we'll see 4 jobs completed, but it's going to take some time. That actually completes the walkthrough part, but I do want to talk about some other DRA drivers. In the maintainer talk on maintainer summit on Sunday, the contributors released a DRA driver for CPU resources. And I have the link at the walkthrough here, where you could use higher since not all CPUs are created equal. Some CPUs are closer to the GPU, so you could align your resources together using DRA. So you could align your CPU, GPU, and NIC on the same NUMA domain, Or if you want, you could request all CPUs, let's say all 10 CPUs are all sharing the same L3 cache. So we definitely could see this. And this is also not in production as well. I was told that it is not GA or stable, but it is something to look into in the near future. Of course, we covered NVIDIA and Intel as well, but I do want to put a link for AMD's DRA driver as well. And also another DRA driver by Furiosa AI as well. Lastly, part of this walkthrough here, there is a video of all the commands we went through. This GitHub page is going to stay up. I'm never going to take it down, so if you ever want to do another walkthrough for this, you can. All you need to do, if you want to use the same bash script to install Kind, is just a RHEL 9, 2 CPU, 8 gigs of memory. Works for this lab here, but I'm sure you could use it 2 gig and maybe 2 core and 4 gigs of memory might work, but typically I'd like to bump it to 8. So anyway, that ends the walkthrough. Does anyone have any questions before we end? Yes, but. Of course, this example is using time slicing, but you could use vGPUs as well. Time slicing, I believe, is the default for it, but I know you could configure, pass on configuration changes, but I don't know what those changes are for the NVIDIA driver. Yeah, question? Device plugin, yeah. So that is the chicken or the egg problem, right? So most likely folks will use device plugins for a while, because that's what's out there. We know that. We know how to install the NVIDIA operator. We know how to use NFD. We know device plugin pretty well, right? It's great for the current devices, but let's say if you want other devices that NVIDIA is creating, like that rack of GPUs that NVIDIA has created, and that is kind of more of the feature. So where you could use maybe a network attached devices as well, that could be used by the cluster, use workloads for the cluster. I see that same issue, or not issue, but the support isn't out there yet for the devices, right? So the standard way for device plugins will probably still stay around for quite a bit. But I know folks in SIG networking for Kubernetes, especially with the Gateway API folks, are looking into how do we use DRA more in the future, because of success of like DRAnet. But so it is very early on. It was just stable. There's a lot of new features for DRA that will actually make it more usable. I could say one provider, I won't say who, will state that they will actually their stable for DRA is actually in the next version when some features of DRA is actually unstable as well. So there's new features that will come up. There's at least 5 that I know of, or I can recall. Yeah, so that will make it more usable for folks. But it really is right now is device plugins. You're right, it is device plugins. Just the upcoming devices that come up will tend to use DRA versus device plugins. But we know device plugins well. Yeah, go ahead. Yes, in the near future. That is actually partitioning is actually an upcoming feature. I don't know what release. Yes, that is one of the key features. I think there's even up to 10 new features that are coming up that's in the works of DRA, but partitioning is one. A question? That's up to the vendor, but the partitioning capability is upstream, but I can't speak to the vendor on that, but I imagine so. I imagine some KubeVirt integrations as well. Because right now, if you use KubeVirt with device plugins, you use vGPUs to pass on those vGPUs onto your virtual machines from KubeVirt. I can imagine that there will be integrations with KubeVirt and DRA and or vGPUs or some type of sharing that we can pass on to virtual machines from KubeVirt.
Is there a list of NVIDIA GPUs that DRA supports?
I don't have a list, but I'm sure there is a list of the supported models. Yes, yeah. I have the GitHub repo for NVIDIA in there, so it might be in there. I also have the docs for NVIDIA for DRA in there as well. NVIDIA docs, if you ever use NVIDIA docs and you know NVIDIA docs, I mean, they may not be in there, but yeah. Any other questions? All right, feel free, question. I didn't get all of it. It was something with DRA that could do something that mission control could do. Is the question about allowing specific access for pods to specific devices? Yes, yeah. So that is in the works as well. There was a working group device management talk yesterday, and they listed out all the in the works features of DRA, and there was like 10 of them that I was not familiar. I didn't know about 5 of them. So, yes, that is in the works. So, the stable core. That's why for 134 release notes they mentioned core DRA is stable, but meaning that a lot of folks are looking for the other features that will be stable in the next releases. So. All right, thank you very much for your time. Hope you enjoyed. VMs will be up for the next few hours. Like I said, run it on your own. All you need is Kind. You want to mention that DRA was actually created, and Kind was used to test it along its creation as well. So if you want a small local cluster, Kind was used in the testing.